Hey guys, welcome again to the Maths Club. If you are just joining us, you're welcome. We've been looking at surface area volume of shapes for a while, and this is the last video before the WAEC past question video. In this video, we're looking at surface area volume of prisms, pyramids, and irregular solids. So if you have not subscribed to our channel, please do so, and like our video. I can assure you that you end up enjoying it. So let's get started. We've established that the solid is a three-dimensional shape and is symbolized by the alphabet A, right, and is a measure of the total area that the surface of the object occupies. We've established that in the previous videos, measured in square units, and then we've said it that for a 2D object or a shape, the area is calculated, and for a 3D object or shape, total surface area is calculated. So we're looking at prism. A prism is basically a solid object with two identical ends and flat sides, right? So it is named by the shape of their bases. We're going to see images of this, and the images will bring life to those definitions that we have made, right? So these are examples: triangular, rectangular, pentagonal, hexagonal, and cube. Let's see some pictures. So look at this. This is a triangular prism. What do you see? The base and the top, they are both triangles. You know, we said that they have identical ends and flat sides. So this is flat side 1, flat side 2, flat side 3, right? And we said that it is named according to the base. You see, the base is a triangle, so it's a triangle prism. See the second one, rectangle prism. See the bottom and see the top, they are both rectangles, right? And you can see the flat sides all around it. Same thing for a cube. The top and the bottom are square, right? And if you look at the sides, I mean, they are flat. Same thing too for this hexagonal. Hexagonal is like six-sided, so you see side 1, side 2, side 3, side 4, side 5, side 6. Same thing too for the bottom. I can see all the flat sides, and you can see for the pentagonal prism. So if I go back to our definition, you say a prism is a solid object with identical ends, two identical ends, and flat sides. Makes sense? Yeah. And is named by the shape of their bases. So in this video, we're going to be looking at a right triangle prism. This, so you can see triangle, triangle, and you can see the base, you can see the perpendicular heights each, and you can see that it makes 90 degrees with it, and this is the length L. Like I said, it's just as if you have a triangle and you're stacking triangles on each other, basically. So if you want to find the volume, remember we said that you find the base area times the height or the length. So the base area here is the area of this triangle, because the base is a triangle, so the base is a right triangle, so that will be half base times height, and because we want to find the volume, we have to multiply by the L, right? So how long does it span? So for the cross-sectional area, what is the cross-section? The cross-section is just like, so if I had like a knife and I cut it across this place, what shape will I see? I cut it here and I'm looking here. What shape am I going to see? Of course, I'm going to see a triangle, right? A right triangle. So what is the area of that right triangle, of that cross section? Is to my normal half base times height. So the cross sectional area is something that's base area, right? And the volume is base area times height. Example 1 says that what's the volume of the right triangular prism below? This thing from NECO 2002. You can pause the video and try this out yourself. So to solve this, we know that the volume, right, is going to be the base area times the height, right? What is the base area? The base area is a right triangle, so that is half base times height multiplying the length. So where's the base? So if I say the given, the base is this guy here, which is 10 centimeter. We're not given the height, right, but we're given this slant side. So I mean, in terms of triangle, because say this is, if these are theta, this is the opposite, this is the adjacent, this is the hypotenuse. So the height is not given, right, but the length is given to be 16 centimeter. But we can find the height by saying from Pythagoras. Let me just do it here. We know that the opposite squared is equal to the hypotenuse squared minus the adjacent squared. So that will be 13 squared minus 10 squared, and that will give me 169 minus 100, which will give you 69. So the opposite would be square root of 69. Great. And that opposite is my height, so that is the h. So we have this, we could say half times the base is 10 times square root of 69 multiplying the length, which is 16. So 2 here 1, 2 here 5. 5 times 16, that will give you 80. So 80 times square root of 69. So if I point that to my calculator, that is 80 root 69. That gave me 664.53 centimeter cube. But did they say we should? I mean, if you look at the options, of course, we know that we are rounding up to the nearest whole number, right? So that would be approximately 665 centimeter cube. So I'll just say to the nearest whole number, or to the nearest volume, basically. Let's see if our answer is correct. Great. Option E. Example 2 says that the diagram shows a triangular prism of length 7 centimeter. So the right angle triangle PQR is a cross section of the prism, and we're told that PR is 5, RQ is 3. The question now says that what is the area of the cross section and what is the volume of the prism. This is taken from WAEC 2001. So I encourage you to pause the video and try this out yourself. So for this, of course, we're given the opposites, we're given the hypotenuse, we have to find the adjacent to be able to find the area, right? So we could say we are given, right, the opposite to be 3 centimeter, the hypotenuse to be 5 centimeter, but we're trying to find the adjacent, which is the same thing as our base, right? And we're told that the L is 7 centimeter. So from Pythagoras, the adjacent squared is the hypotenuse squared minus the opposite squared. Of course, you should know this. So this is 5 squared minus 3 squared, and that will give you 25 minus 9, which is 16. So our adjacent is square root of 16, which is 4 centimeter. So these are adjacents, which is our base. So to answer question A, the area of the cross section would just be half base times height, right? And our base is the adjacent, which is 4, and our height is the opposite, which is 3. So so this is 6 centimeter squared. For the B part, the volume, that would be the cross-sectional area times the height, and that would be, we already have the cross-sectional area, right, or base area, anyone you want to say. You know, we said the cross-sectional area is the base area, so that is 6 multiplying the height. What is the height? 7. So 6 times 7 is 42 centimeter cube. So this is the solution to this question. Let's see if we're correct. Great. So 6 centimeter squared and 42 centimeter cube. Next, we're looking at the pyramid. Off the top of your head, can you name one pyramid in the world? Yes, most likely you will have said all those Egyptian pyramids, right, where they used to bury their kings. So that is a good example of a pyramid. Or if you are a bit older, you will know the granite pyramids in all those Kano states of those years, right? I don't think they do it again. But a pyramid is a solid shape with triangular faces meeting at a point. What point is that? The point is called the vertex. The shape rests on a base, which can be square, triangular, rectangular, or other polygon. Most likely, most of the pyramids that we see, I stand to be corrected, but I think it is maybe square or triangular, one of the two. Right, yeah, so you can see the triangular with 4 faces, 4 vertices, and 6 edges. So you can count it. I'll just do for one. So the face, this face 1, face 2, the other side face 3, and then the bottom face 4. Vertices are the points where they meet. So this 1, 2, 3, 4 vertices, and edges is like this guy 1, 2, 3, 4, 5, and then the 6th one here. So you can count for the other ones. So pyramid on a square base, so you can see this, because it's a square, this length is the same as this length. You can see the perpendicular height. Just so we know, right, this point where they meet, when it comes down here, it is at the intersection of these two. So you have something like this, and you have something like this. This should have been a straight line. So this point here, it would extend here. This is where it will meet, right? So from here to the midpoint is the H, right? So it doesn't just start from any point on, it starts from the intersection of these two lines, and you see that application very soon. So this is the slant height, this is the vertex, and this is the base. Of course, the base is a square. So for the volume, right, volume is basically base area times height, like we always say. So the base area times height. So like I did for the cone, you know, I said if you look at that cone, it's like as if they divided that cylinder into 3 places. If you watch that video, 1, 2, 3. So anytime you see something like this, right, it's always like 1/3. That's the way I always pick it. So 1/3 times the base area. Base area is a square, so that will be L squared times the height h. So once you picture that is a cylinder that has been like maybe cut into 3, based on that description I did, then you always remember that whenever I see something like this, it's always 1/3. So example 3 says that the base of a pyramid is 12 centimeter by 12 centimeter square. If its height is 20 centimeter, find the volume of the pyramid. This is from WAEC 1999. I assume that you will pause the video and you try it out yourself. So for this, we know that the volume is 1/3 base area times height, right? So for the base area, is so that will be L squared, and that will be 12 squared, which is what? 144 centimeters squared. The height is given as 20 centimeters, so we can find the volume. So that will be 1/3 times 144 times 20. 144 times 20 divided by 3, that's 960 centimeter cube, and that will be option B. Great, these are simple as it comes. Then we go to the base complex, which is a right pyramid is on a square base of side 4 centimeters. We know the sides of our square. The slanting side of the pyramid is 2√3 centimeter. Calculate the volume of the pyramid. This is from WAEC 2001. Let's solve this one together. So look at this. I have to, you know, I said, look at, they said the slanting side. This is like the slanting side, right? The slanting side, or the slanting side. But what we need is the height, right? We need to find this height h. This is the height that we need. So let's see. So if I connect these 2 points, let me see, I connect these 2 points here. Great. And I also connect these 2 points. So let's see, connect these 2 points. Great. So this line here would continue to extend until it touches the intersection point here. Great. So the, like I said, I told that the vertex would come down to the intersection point of these two. If you have cash, right, you can get a pyramid like this and try to picture it. So what do we know? We know this length. We know this length, and it's a square. So each of these angles are 90 degrees, right? 90 degrees, 90 degrees, and of course, because when we talk about parts of a square, when they intersect, this side here will be the same length as this side, and this side here will be the same length as this side. Like they will all be the same length because it's a square, right? So if this is 5 and this 5, this guy will be 2.5, 2.5, 2.5, 2.5. We know that already. So I can find the length of this guy, right? When I find the length of this guy, I will divide it by 2. Of course, also 2. This line will also make a 90 degrees with this place here. These are things that you might not really be able to picture because we're not looking at the real thing, but I'm telling you, so just right. So this place will also be 90 degrees. Once we know this side, we know the slant side. This slant side has been told to be 2√3 centimeter. We know this slant side. We know this side. We can also use Pythagoras to find the height. So let's take one at a time. Let's first find this length. So if this is A, this is B, this is C, this is D, right? So I could say, so just say from Pythagoras, BD all squared is equal to CD all squared plus BC all squared, right? So BD squared is equal to, what is CD? CD is L. Our L is 4 centimeters. So that would be 4 squared plus 4 squared, and that would be 16 plus 16, and that would be 32. So BD is square root of 32, which is, if you press that in your calculator, that will give you what? That would be 5.6, let me just say 66 centimeter, right? Approximately. Correct. So we know BD. So let's say this is point O, right? So therefore OB, length OB would just be length BD divided by 2, right? So that would be 5.66 divided by 2. So if I divide this by 2, this would be 2.83 centimeter, right? So this OB. Now that I know the OB, I can now find let me just call this E. I can now find the OE, right? So also from Pythagoras, the hypotenuse squared is equal to the opposite squared plus adjacent squared, but I mean I'm trying to find the opposite squared, so I'll just say the opposite squared, which is OE all squared, is equal to the hypotenuse, which is EB, right? So EB all squared minus the adjacent, which is OB, so minus OB all squared. So what is EB? EB is 2 roots 3 all squared minus our OB is 2.83 all squared. So let's now plug that into the calculator. So that will be minus 2.83 all squared. So this gave me 3.9911. So our OE will just be square root of 3.9911. So if I find the square root of the answer, that will give me this is almost 1.998 centimeter, right? Approximately. So I have the OE, which is the height. Now I can find the volume. So to find the volume, you have to look at the objects, right? Whenever I see this object, always remember 1/3. So that will be volume is equal to 1/3 of the base area multiplying the height, and that is 1/3. The base is a square, so that is L squared, which is 4 squared times 1.998. So that's 16 times 1.998 divided by 3. So that's 10.656 centimeter cube. So let's look at the options and see which of them relates. Yeah, that is option B, 2/3. 2/3 is 0.67, so 10 plus 0.67, that is 10.67. I have 10.656. The difference is because of all of these approximations. You know, we did square root of 32. We took just a portion, right? All those approximations will show in the final answer. So our answer should be option B. Let's see if we're correct. Great. Example 5, we're now talking about irregular solids. Solids that don't have irregular shape like we know. So look at the diagram. Is a portion of a right circular solid cylinder of radius 7 centimeter and height 15 centimeter. The center of the base of the cylinder is Q. So this is the center of the base of the cylinder. This is Q. This is the point. So it's at the center. While that of the top is B. So this is the center B. Where angle ABC is 120 degrees and angle PQR is 120 degrees. Calculate, correct to 1 decimal place, the volume and total surface area of the solid. Take pi to be 22/7. Let's solve it together. So look at this diagram, right? What we are trying to find is the volume. You know, this is a cylinder. So imagine we find the volume of that full cylinder. They will now find the volume of the portion that is cut out, right? So if I have the volume of the full cylinder minus the volume of the portion that is cut out, that will give me the remaining volume. Yeah, great. So what do we know about the portion that is cut out? The portion that is cut out is, look at it. If I draw this place here, let me see, if I draw something like this to this point here, you realize that this is a sector, right? So we can find the area of a sector, can't we? Great. So if I find the area of a sector and I multiply by the height, would that give me the volume? Yes, it will. So the volume of the cylinder is pi r square h, right? And that will be 22/7 times 7 squared times 15. So one of the 7s will cancel out. So this is 22 times 7 times 15, and that will give you 2,310 centimeter cube. Right, so that's the volume of the cylinder. Now for the volume of the cut out portion, so the volume of the, let me just say, I mean, if you look at it, it's actually a sector, right? So we could just say volume of the would that be correct? So let's just say cut section, right? Let's just say cut section. That would be area of a sector multiplying the height. An area of sector is what? Theta over 360 times pi r squared multiplying h. What is our theta? Theta of the sector is 120. So that will be 120 over 360 times 22 over 7 times 7 squared times 15. 7 will cancel one of the 7s. This will cancel. This will be 3. 3 will cancel. This will be 5. So that will be 22 times 7 times 5. And that will give you 770 centimeter cube, right? So we know that the volume of the, how will I say it, irregular solid, right? So the volume of the, let's say, irregular solid is volume of the cylinder minus volume of the cross or the cut section. So that is 2310 minus 770. 2310 minus 770, and that will give you 1540 centimeter cube. Great. So our answer says that we should do it to one decimal place. So to one decimal place, that would be approximately 1540.0 centimeter cube. Right, so I have to put it at 0. In order that we should find total surface area. Great. So if total surface area, if this is the, this is the minor arc, this one here will be the major arc. So if I can find the area of this major arc, multiply by 2, because I'm in the same angle, so that will multiply by 2, right? Then, so for the cut section, right, you can see even the cut section parts, right, is the one for this major sector, right? And we know that when we're dealing with this on that cylinder, we said for the curved section, the area of the curved section is 2 pi rl. If you remember that video where I broke up the top, the bottom, and then the side, right? Remember, it became a rectangle, so that was 2 pi rl. But it is not complete, so we have to just take the theta, or the portion of the one that we have, right? You said that will be theta over 360 times 2 pi rl, right? Then we'll have found the surface area of this guy, surface area of the bottom, and surface area of this curved portion. It will now remain this place here, right? This guy is 15 centimeter, this guy is 7 centimeter, this guy is 7 centimeter, this guy is also 15 centimeter. So, and that is really a rectangle. So we'll add it to the area of this rectangle and the area of the rectangle, and that will give us our total surface area. Let's see it in practice. So I had to bring it out and duplicate it again so that we'll see what we are doing. So the total surface area is 2 times the area of the sector, which is the major sector, this plus this, plus the area of the curved surface, plus 2 times the area of the rectangle, right? So this will be 2 times theta over 360 times pi r squared, plus area of the curved surface area, that will be theta over 360 times 2 pi r l, right? We established that, and then plus 2 times l times b, right? So 2 times this theta here is not this one theta, is the major one now, so that will be 240 over 360 times 22 over 7 times 7 squared, plus 240 over 360 times 2 times 22 over 7 times 7 times 15, then plus 2 times the L and the B, this 7 times 15, so 2 times 7 times 15. So let's simplify in a simple way. This will cancel this, one of these guys will go, right? How else can we do it that would not lead us into confusion? So 6 here 4, 6 here 6, 2 here 1, 2 here 3. So I have 4 times 22 times 7 divided by 3 from this first guy, and that is 616 over 3, plus this will cancel this, 12 here 2, 12 here 3, 3 here 1, 3 here 5, 7 will cancel 1 with 7, so that will be 2 times 2 times 22 times 5, and that will give you 440. So plus 440 plus 2 times 7 times 15, that will give you 210. So 210 plus 440 plus 616 all over 3. This gave me 855.3. I mean, they said to one decimal place, right? So I had 0.33. So this is approximately 0.3 centimeter squared to one decimal place. So you need to just understand what you're doing in this particular thing. You actually need to understand. That's why it's a flow. You can't just jump at one video. You have to start from the beginning and build up your knowledge base. Right, so we saw the area of the sector, this major sector, we added the two of them together. The curved surface is not entire, so we just took a percentage of that curved surface. That was why we used theta over 360, then this rectangular face. By the time we add all of them together, that'll give you total surface area. That is the area of the parts that are exposed. Let's see if our answer is correct. So we have 1540.0 centimeter cubed to one decimal place, great, and 855.3 centimeter squared to one decimal place. Correct. Example stated that a solid shape is formed from a combination of a cone and hemisphere, such that the height of the solid is 6 centimeter. If the radius of the hemisphere is 1.5 centimeter, calculate the volume of the solid. Correct your answer to 3 significant figures. This is from NECO 2004. I hope you maybe tried it out by yourself, but let's see. So we are combining an hemisphere. So an hemisphere is like a bow, right? So this is like a bow, and we are putting a cone on top of it, so something like this. Right, great. It now says the height is, so from here to here, is 6 centimeter. The radius of the hemisphere, remember we said for the hemisphere, the height of the hemisphere is the radius of the hemisphere, because it's taking half. So here is 3/2 centimeter, right? Same as 1.5. Then that means that the height of the cone is 4.5 centimeter. So calculate the volume of the solid and correct to 3 significant figures. So for us to find the volume, we have to find the volume of this hemisphere and add it to the volume of the cone. So the volume is volume of hemisphere plus volume of cone. So volume of hemisphere, for a sphere, the volume is 4/3 pi r cube, right? But for an hemisphere, that is half. So that will be 2/3 pi r cube. And then we know our volume of cone to be 1/3 pi r square h. Remember how we arrived at this? Remember when I told you, when it's just know 1/3. So our v here is 2/3 pi r cube plus 1/3 pi r square h. The radius of the hemisphere will be the radius of the cone. We don't need to bother ourselves about that. So I can factor out pi r squared over 3, right? So this will give me 2r plus this will give me h. So this is 22/7 times our r is 3/2 all squared, right? Then I will divide, or I'll multiply by 1/3. Basically, I can multiply by 1/3. It's the same thing. So open brackets, 2 times 3/2 plus our height. Now this h here is the h of what? Is it the h of the entire height or the h of the cone? It's the h of the cone, because the h is coming from the volume of the cone. So you cannot, if you use 6, you are wrong. You have to use 4 and the half, and that is 9/2, right? So plus 9/2, close the brackets. So this 22/7 times 9/4 times 1/3 multiplying, so 2 times 3/2 plus 9/2, that will give you 15/2, right? So now let's plug all of this together. So this is 22/7 times 9/4 times 1/3 times 15/2. So this gave me 17.67. Let me say 679. Let me see how many significant figures this, so we should use 3 significant figures. So 679 centimeter cube, right? So 3 significant figures. This is significant figure 1, significant figure 2, significant figure 3. So because the next guy is greater than 5, so that will add 1 to it, and that will give me 17.7 centimeter cubes. So these are approximately 2, 3 significant figures, and that will be option D. Let's see if we're correct. Great, option D. So example 7 now says that a solid is made up of a cylinder of height 20 cm and diameter 14 cm with a clone of slant height 10 cm on top as shown in diagram below. Calculate total surface area of the solid. Take pi to be 22/7. This is from NECO 2002. Let's solve it together. So to find the total surface area, we have to find the surface area of the cone plus the surface area of the cylinder. For the surface area of the cone, if you look at it, the base of the cone to the circle would not show because it is directly on top of the cylinder. So what we'll be looking at is the curved surface area of the cone, right? Because the bottom will not be showing. If the bottom was showing, we'll have said plus the area of the circle. Now for the cylinder, the top will not show because the top has been capped by the cone. What you have to be the curved surface area plus the area of the circle under. The circle under will show. So by the time we find this and we find this and we add them together, we would have our answer. Now for the curved surface area of the cone, the formula is pi RL, and then for the surface area of the cylinder, the formula is 2 pi RH, and then for the area of the circle, that is pi R squared. So let's plug everything and see. So this would be equal to pi RL plus 2 pi RH plus pi R squared. So what do you notice? None of them pi R is common. So just factor it out. So that will be this divided by this give me L plus this divided by this will give me 2H plus this divided by this will give me R. Now we know that our L is what? Our L is the slant length of the cone, which is 10 centimeter. H is the height of the, so the 2 pi R is coming from the cylinder, so that will be the height of the cylinder, and the height of the cylinder is 20, so 20 centimeter. And then our R is the radius. This, they give us the diameter here, 14, so that will be 14 divided by 2, which is 7 centimeter. So this is 22 over 7 multiplying our R is 7, our L is 10 plus 2 times 20 plus 7. So this will cancel this. This will be 22 open brackets 10 plus 40 plus 7. So this is 22 times 57. If you point at your calculator, that will give you 1254 centimeter square. Let's see if our answer is correct. Great. So with this, we've come to the end of anything that has to do with surface area and volume of shapes. In the next video to this, we'll be looking at WAEC past question from 2014 to 2024 that covers this topic. I'll see you there. Bye for now.